तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will talk about programmable logic devices. Programmable logic devices are building blocks which are used to realize digital systems. They can be used to design combinational logic, and also they can be used to design sequential logic. Today we will see some of the basic PLD programmable logic device types and take simple combinational logic examples. In a later lecture, we will talk about sequential circuit implementation of using programmable logic devices. What is programmable logic device? Now, we saw in the lecture on multiplexers, combinational logic design using multiplexers. It is easy to make devices, the circuits function based on a hardware available, rather than go to the corner map minimization technique of reducing the number of gates. So, as the circuit complexity increases, we do not want to go on building gate level logic, we go for higher complex hardware and try to map the given circuit specification to this hardware available. Now, if the circuit becomes more complex than can be accomplished using multiplexers, that is one reason. Another reason is sometimes you want a variation from multiplexer based design, you want some other type of design. Whatever is the case, either of these two cases of either increased complexity of circuit or you want an alternative to multiplexer based design, we have another set of hardware available which are called programmable logic devices. These are devices with again gates and OR gates in large number available in a single hardware, and it is up to you to use them any way you like to realize the function that you want to realize. Another feature of the programmable logic device is that these are, as the name suggests, these are programmable. That means I can change applications. I can design it for one application, then I may decide to change either the application or specifications of the given application. In either case, I can go and redo the design on this programmable logic device. And these programmable logic devices are available also as erasable programmable logic devices, EPLDs, and when you have an erasable property, you can reuse the hardware either because you made a mistake in the design or because the specification is changed or you want to go for a totally new application. Whatever is the reason, you may be able to erase the function of that PLD and then replace it with a new function. So, these are the reasons why you go for PLD as an alternative to multiplexer based design for logic implementation, combination logic implementation. There are basically 3 types of programmable logic devices. One is called the ROM, read only memory, all of us know that. That is, you can store combination of input variables to generate different outputs. In other words, ROM is nothing but a truth table in the hardware form. In a ROM you have the, in a truth table you have the inputs and combinations, and for each combination the output tells you whether the output is 1 or 0, and you may have several outputs. So, ROM is exactly that. ROM will have inputs. For example, I may have A, B, C as inputs, and I may have 2 outputs called F1 and F2. I can, for F1 and F2 in the truth table you have rows on which they are 1, rows on which they are 0. So, I can map all those zeros and ones for F1 and F2 in this hardware, then it becomes a implementation. So, this is a ROM. So, ROM is nothing but a hardware truth table, hardwired truth table or hardware truth table as you will, and the combination for which F1 is 0 and combination of the input for which F1 is 1, they will be stored in this ROM, and whenever a particular combination of ABC occurs, corresponding output 1 or 0 will come out of the F1, similarly for F2. Now, let us take a simple example, the same full adder. I will not write the whole truth table, you are familiar with the truth table. In the full adder circuit, 1 bit full adder, these inputs are AI, BI, CI minus 1, outputs are SI and CI. We know that SI is 1 for one, 2 min terms, 1, 2, four and 7. For min terms 1, 2, 4 and 7, sum is 1. For other min terms 0, 3, 5 and 6, sum is 0. Similarly, with the carry output, we know that, so we will call this okay, this is f. So, this is f of function is 1 for input 3, 5, 6 and 7. Input combinations 3, 5, 6, 7, namely min terms 3, 5, 6, 7. The carry output is 1, for the rest of the min term combinations the carry output is 0. Now, this is a truth table implementation directly without making any simplification. We read this from truth table. I did not write it again because we had it from a lecture on the previous lecture on multiplexers, the truth table for sum and carry for inputs A, B, I and C, I minus 1. From that truth table you can read this, because this is a standard thing, all of you are familiar with this from your first course in digital design. So, that is why I do not want to spend more time on writing this. Now, all I have to do is to take this device, program the device such that whenever the input combination or min terms 1, 2, 4, 7 occurs, the output will be 1 for sum. Similarly, for the rest of the input combinations or min terms, output will be 0 for sum. Likewise, whenever the min term 3, 5, 6, 7 or the input combination 3, 5, 6, 7 occurs, we will have the carry as 1, for rest of the input combinations the carry will be 0. So, that is why this is, I am calling it as a hardwired truth table or the truth table in the hardware form. What is inside this ROM? After all, how do you generate these minterms? By combinations of A, B and C, and how do you generate the output? Output is by combining the minterm. So, you need an AND gate array in order to combine this A, B and C in different to get minimum different minterms, and OR gate array in order to combine the different minterms to form the output. So, basically it will consist of an AND array in which the inputs will be A I, B I, C I minus 1. Output of this AND array will be corresponding to the minterms. I am calling them 0, 1, 2, actually you should call them in textbooks you will see them as M0, M1. If you want to call them M0, M1, M2 is fine with me. Minterms, and OR gate array in order to combine these minterms into the required sum and carry. Usually a symbol of OR is put here indicating the minterms are combined in an OR gate. This is only a symbolic representation. I am not showing the actual gate connections inside the AND gate and OR gate. So, this is an OR array, this is the AND array. I am not showing the AND gates, it is only a symbolic representation. This is an OR array. So, as we said, now 1, 2, 4, 7 minterms, all the minterms are available, out of which the minterms 1, 2, 4, 7 is the sum, and minterms 3, 5, 6, 7 3, 5, 6, 7. So, with this array of AND gates, we are generating the minterms M0 to M7, and with this array of OR gates, we are generating Si and Ci, which are functions of the minterms M0 to M7, and these minterms are the combinations of A, B and C, A, B, A, Ci minus 1 in this case. For example, we know that M0 is nothing but A bar, B bar, Ci bar, Ci minus 1 bar, M1 is A bar, B bar, Ci minus 1, M7 is for example A, B, Ci minus 1. Now, this whole thing can be gotten in one chip, that is why it is called programmable. The reason it is called programmable also, I can have different functions instead of Si and Ci, instead of implementing a full adder, I can have some other function in which several other minterms may be involved. I can reconnect my input to the OR gate. How many minterms will be there depends on the number of inputs. In this case there are 3 inputs, so there are 2 power 3 minterms. In general, if there are n inputs, we will have 2 power n minterms. Number of outputs will depend, number of OR gates will depend on the number of output functions to be implemented. Now, we are not showing inside of this, as I said, there is an array of AND gates, 2 power n AND gates in order to generate each of these minterms, and an array of OR gates, in this case only 2 gates whose inputs are connected to the various minterms. Now, why are we calling it programmable? It is a fixed thing. in order to make it programmable, I should have a technology by which I can change the connection. These OR gates should have the connectivity which can be changed. If you do not have the connections which can be made or unmade, you should be able to either connect the OR gates. These min terms are fixed. All the min terms will be generated. The moment you have the number of inputs, the outputs are fixed. But in what way are you going to combine these min terms is the programmability. So, this is a fixed AND gate array and programmable OR array. What is the programmability? What is the programmability about this? The programmability comes because I can give different inputs to the OR array, but that means I should have the technology. That means I should have the gate inputs which can be switched between various min terms. That will not go into the technology of this. That is not in the scope of this design. But I want to tell, in that case you cannot call it ROM, read only memory. When you say read only memory, it is a fixed program read only memory. Once you program it or make the connections to the OR gate, they stay fixed, they stay constant, you can't change them. So, that is the ROM, read only memory. But once you have the programmable feature where I can have the choice of programming the min terms as the inputs to the OR gate, such a device would be called a programmable ROM or PROM. That means I should have some technology by which I can make or break or connect or disconnect different min terms as the input to the OR gate. As I said, the scope of this lecture will not take us to the technology aspect, but you should know there is a technology that exists. But suppose I program it and I do not like the program for some reason, either because I made a mistake or because I want to change the specification slightly, or because I want to totally remove this application and use the same device for some other application. That means I should also have a property of erasing the program. Once I have a program, I should be able to remove the program and reprogram it for some other application or some other configuration. So, I need also an erasable programmable ROM. So, this is the read only memory where the fixed AND gate fixed. Even though the OR gates are programmable, the connections are fixed, I can't change it. That is a ROM. They are fixed ones, self factory programmed. It comes programmed from the factory as it is, you use it as it is. This is field programmable. That means you have the device and the capability to change the input to the OR gates from various min terms. It is called field programmable. That means I can make the connections the way I like. But once I make it in the field, if I cannot change it, I can make only one set of connection. I need one more feature where by which I can remove the program and redo it, that is called field programmable, erasable programmable, that is called erasable programmable. Erasure can come out of shining ultraviolet rays called UV EEPROM. You can erase the device after programming it by shining an ultraviolet light on the device. You might have seen EEPROMs with a window covered with glass. When you try to open a computer or something, microprocessor kit in your lab, you will find a window. This window is the window through which you shine the light. That is old technology. Today we can do it electrically. EEPROM, electrically erasable program, by applying electric pulses, current pulses, I can erase. Even these things require the device to be removed from the circuit. You erase the whole thing. I can't selectively change the program. Supposing I made it for one application, I change it for, I can change it for the entirely new application. On the other hand, if I have a minor change in my application, I want to selectively change some programming, it is not possible in these two techniques of erasure. In the erasure, you have to erase the whole thing by ultraviolet rays, you have to erase the whole thing by electric pulses. Today we have a device called EA from electrically alterable programmable read-only memory, wherein when the device stays in the circuit without having to remove the device from the circuit, when the device stays in the circuit, you can selectively alter the programming of the device wherever you want to. These devices are also called flash memories, you might have heard of this term. These are electrically alterable programmable read-only memories or flash memories, wherein I can keep the device in the circuit and selectively alter the programming of the device. So, that is the most widely used device today. ROM is used in large number of applications because of its size of the ROM required is proportional to the number of inputs and number of outputs. Number of inputs increases the number of min terms, and number of outputs increases the number of OR terms. The AND term explosion is exponential. If I had one more input instead of 3 inputs, if I had 4 inputs, I will have 2 power 4, which is 16 min terms. So, every one extra input I need a 2 power addition in the number of min terms. On the other hand, OR terms will increase only by the number of outputs. So, in general for n input m output circuit, I need 2 power n times m is the size. Size is given in bits. This is the size of the ROM. Size of ROM for n input m output device, we need the size will be 2 power n times m. Remember that input increases the size exponentially, whereas output increases linearly. This is a very simple technology, and today, as I said in the beginning, the cost of this gate is not at all considered. We have semiconductor complexity which are running into millions of gates, billions of transistors, and a device like a 1-bit ROM can be very easily made. So, you do not have to really optimize on this, except in very huge applications where the number of inputs are extremely large and this becomes exponentially large, and we do not want to use that size just like that, because even though it is available, semiconductor area is available, it increases the cost of the device or the cost of the whole circuit or the device system you are designing, plus you will be unutilized. You have only a large number of input table min terms, but how many of them are used? The number of min terms being used by a given function will be usually very small. Any function, whether it is 3 input function, 4 input function, 5 input function, or even 57 input functions, whatever number of inputs, a given output will have only a few selected terms out of it. That means most of the min terms that are generated will not be used in the output. This is a waste of hardware or silicon real estate, as I call it. So, for these two reasons, that is underutilization of the size and an exponential growth in the size for very large applications, we want to have another alternative. The second alternative to the programmable logic device family is called programmable logic array. Or PAL for short, programmable logic array, PLA for short. Now, The difference between a ROM and a approach and a PLA approach is simple. Again, it is programmable. In the sense, I should be able to change my connectivity either for making minor changes or because I want to make a correct a device design bug, a design bug to be corrected, or I make a minor change in my solution, or totally remove the application and put in a new application. So these are also available as erasable programmable. This is also erasable available, so we call EPLDs. PLD stands for programmable logic device, EPLD stands for erasable programmable logic device. Anyway, that is for all devices, that is common, so I will not write it separately for this. Now the question is, what is the difference between PROM or a ROM? We will call it ROM, that is most, even though it is a PROM. We will use a programmable read only memory, but generally it is called ROM design, ROM based design they call, they do not say PROM based design, you do not hear that term. PLA and ROM, what is the difference? I said number of minterms are generated, many of them are not used, especially when the inputs are large. So can we now generate only such of those terms which will be used, or can we only generate a few terms, product terms, which will be used in my output OR gates? In this case, we did not have to do any simplification. The truth table directly implemented in hardware form. So that is why I called it hardwired truth table. But in this case, in the programmable logic array case, I will use a few select product terms in order to generate the required output. That means I do not have to have a whole set of AND gates 2 power n, I will have a fewer number of AND gates and generate a bunch of product terms which will be used in the implementation of the final output. Now the question is, how do you select what product terms to be used? There are two things. One is I am going to reduce the number of AND gates, so the size of the device is going to reduce for a given application, or when the number of inputs are very large, I do not have to generate all the AND product terms or min terms, but I will only generate a few product terms. You will have to decide what product terms to generate. That will require corner maps. I cannot do guess, I cannot do a guesswork of identifying the product terms to be used in the final. So what I do is to given function, given problem or functions I will say, because I am going to do more than one function, are simplified to a certain extent to sum of product, form. Sum of product is where you have to have a few product terms whose sum will be the output. In doing so, what we will do is I am going to generate a few product terms. So this will be the configuration of the programmable logic array. I will have inputs, I will call them A, B, C. Normally I will require 8 product terms as min terms if it is a ROM approach. Let us say in this case I will have only 5 of them. Instead of calling them M0, M1, M2, M3, M4, I am going to call them P0, P1, P2, P3, P4. P stands for a product term, M stands for a min term. You know the difference. These things you would have learned from the first course in the digital design. Product term need not contain all the inputs, or it is either in the form true form or complement form. A min term should contain all the inputs either in its true form or complement form. Product term may contain some or all of these inputs. Now I am going to have as an example 5 product terms, and I am going to have an OR combination which will combine my product terms to generate the required functions F1 and F2. So in this case I am going to say this is an AND array, but it will not have 2 power n min terms. This will have only less than 2 power n AND gates. How small depends on the output terms and given number of inputs, and these things are combined the same way as we did in the previous case by an OR array. There is no change in this. So, instead of having a fixed AND array which will generate all the min terms and a programmed or programmable OR array in which I will program the inputs of the OR gate, I am going to have a programmable AND array in which I will program the product terms the way I like and combine them again in a programmable OR array by which I can selectively use the generated product terms in order to realize my outputs. So, this is called programmable AND and programmable OR. Programmable AND array and programmable OR array. How do you select P0, P1, P2, P3, P4 depends on the functions themselves. I need to do a little bit of simplification in order to get them. One other thing I would like to do is, which is very interesting, when I select P0, P1, P2, P3, P4, I will select them such that they are as many of these things are common to the two outputs. For example, if I generate one of the terms P3 as common to F1 and F2, it will be used 2 times. My idea is to use the hardware to the maximum possible extent. That is my idea in my design. So, if I can simplify the product term, simplify my input functions or my output functions F1 and F2 using the inputs ABC, such a way I will have as many common terms as possible, then I can make an efficient implementation of F1 and F2. We will see an example in this case. I am not going to do the corner map because, as I said, this is something which you must have learned in my previous course. So, I am going to take 3 functions F0 or F1, we will call it F1, F2, F3. We have been calling F1. F1 is xy, x bar z. F2 is y prime, x bar c. F3 would be xy, y bar c. This will be the, how do I get this? I have an input of ABC, XYZ and an output of F1, F2, F3, and I want a PIL to be used for this function, programmable logic array to be used for this. How do I get F1, F2, F3? From the problem specification, either they have been given to me in this form or they gave me in some other form like a truth table or a tabular form, from which I got this by simplification using corner map. I am not showing that step because that is a too trivial for you in a second course on digital design. What is interesting is though the terms which are common. X bar z is common. So, how many terms would I use if I do not have common terms? I would have generated 6 product terms, P1, P2, P3, P4, P5, P6. Now, since these two are common to F1, xy is common to F1 and F3, I am saving on one product term. X bar z is common to F1 and F2, I am saving on one product term. So, I will now use only 4 product terms, 1, 2, 3, 4. From 6 product terms, I am going to use 4 product terms, saving 2 product terms. How did I get it? This, in this case, as I said, the function was given to me. It could have been simplified, or sometimes you may have to be careful in simplifying it yourself. You do not oversimplify. Sometimes in a corner map approach, the traditional approach is to simplify to the minimum possible form. I would minimize such that I lose the minimum number of AND gates, the minimum number of OR gates and minimum number of inverters. In this case I will not do it. In this case I will look for common terms, even if it comes to be more terms, as long as there are more and more common terms, I will prefer that option, because in the end it is going to give me less hardware. That is the spirit. What I am trying to say is, if I had reduced it, I might have gotten 5 terms, let us say, but by keeping some terms not reduced, I am getting 2 pairs of common terms, which means I am going to use only 4 gates, AND gates. So 4 AND gates is preferable to 5 AND gates. So that extra step of simplification from 6 to 5 is not worth it. So this is a technique you have to practice. I am not going to go into that into further detail. So this will happen now. That means I will have my x, y, this is how it is connected, x, y, z, x bar, y bar, these are all common inside. The PAL will have all this. So my first product term, I will have P1 will be xy. So this is x, y, P1, P0. Second product term would be x bar z, P1, I am going to call this P2, y bar, and this will be my P3, y bar z. So 4 product terms P0, P1, P2, P3 feeding into 2 OR gates, 3 OR gates. First F1 is P0 or P1, this is my F1. Second term would be, second term F2 would be P2 and or this is same as P1 or P2. F3 would be, this is xy is same as P0 and P3. So now this term is common to 2 terms of the output, this product term is common to 2 terms of the, this is common to 2 of the outputs, and these 2 are single. So this is F1, F2, F3. This is how you do this, F1, F2, F3. Now the whole device will be available to you as a single package. You don't know what is inside this. This is the AND array along with the inverters of the input, and this is the OR array. So as far as you are concerned, 3 inputs x, y, z giving rise to 3 outputs F1, F2, F3. So this is also part of the array, this OR gate. Like that. And the fact that we have simplified such that common terms are available between different F1, F2, F3 functions, I can reduce the number of product terms I need to generate. That is the trick in programmable array logic design, programmable logic array design. You simplify such that as few product terms are possible totally, not for individual functions. That is the only thing. Otherwise, that means I am using my number of AND gates is reduced. There are only 5 here, 4 here, instead of for 3 inputs I would have used 8 normally. I would have used 8 normally. This is only 4. There is no reduction in the number of OR gates. So there is a reduction, and whatever AND gates are used are more fully used. I am using them better. So, the silicon is not wasted. This is the output function. This approach is programmable logic array approach, which is slightly better than PROM approach. In the case of ROM, PROM or EPROM, UV-EPROM, EEPROM, I told you that it is not in the scope of this lecture series to talk about the technology of these devices, how exactly the making of the contacts is made, how is an erasable programmable ROM, what is the device that makes programmability to be erased, and what is the difference between EEPROM and EEPROM. All those things I deliberately left out because it a lot of device physics and device theory we have to get into. But on the other hand, with the programmable array, programmable logic array I have talked about in the last few minutes, I want to give you one technique. Is slightly, it may look like it is also device level, but it is not really, it is really a circuit technique. So, I want to talk a little bit about the hardware of the programmable logic array, not so much because I want to tell you how the devices are made, but more because it has an interesting circuit aspect to it. And since the circuit, the designers should also completely know the circuit implementation aspects of a programmable device, we will spend a few minutes on the actual way in which the programmable logic array designs are implemented. Even though I drew an AND gate array and an OR gate array in the example, in practice you do not make AND gates and OR gates within a chip, within a programmable logic device chip or programmable logic array chip. There are not AND gates and OR gates. They generally use one type of gate, either a NOR gate or an AND gate. NOR gate and AND gates are known as universal gates, and for reasons of technology they either prefer NOR gates or NAND gates. And let us say this device we are talking about, programmable array logic, programmable logic array device we are talking about uses only NOR gates throughout. That means I should be able to implement my AND gate array, OR gate array, everything using my NOR gates. How it is really done within the circuit, I will just like to explain to you briefly. Consider this diagram. This is a line or a bus you call it, connected to a voltage, positive voltage. There are two junctions in which we can either make the junction or not depending on these devices. A and B are the inputs, F is the output. Actually this is what it is going to look like for you from a user point of view. We do not know what is inside this. So, there are two inputs A and B and output F connected to a positive voltage V, and now when both are 0, A is 0, B is 0, these switches are nothing but MOSFETs, N channel MOSFET. So, N channel MOSFET will conduct when the device is the gate voltage is high, and it will be cut off when the gate voltage is low. So, we will only talk about cutoff and saturation region, we will not talk about the triode region, etc. This is not a device theory class. So, this N channel MOSFET can be turned on or turned off, let us say, by putting a voltage here. Putting a voltage 0 here will turn off this device, putting a voltage 1 here will turn this device on. So, when both are 0, both the connections are not there, that means these both are turned off. That means the entire voltage V appears at the output F. So, when input is 0 0, the output is 1. Even when one of these devices is on, either because A is high or B is high, whatever is the case, as soon as one of these devices is on, there will be a ground path because this is connected to ground, this bus line is connected to ground through the device. The device is on device, bus connected to ground. If A is on, if B is on, bus connected to ground through this, and both are on, of course, is going to be connected to the ground. So, if A is on, A is 0 or B is 1, or B is 0, A is 1, either case the output is going to be 0, and also when both are 1, output is going to be 0. That means I can realize an output f as 1 0 0 0 for input combination 0 0 0 1 1 0 1 1 by this arrangement, and this is nothing but the characteristic of an NOR gate. All of you know that complement of OR gate. OR gate has a 0 1 1 1, NOR gate is a complement of OR gate, so 1 0 0 0. So this is circuit symbol for that. Now this is another symbol. These two are symbols. Two inputs inverted gets a NOR function in an AND gate. In an OR gate, output inverted gives you a NOR function. Both are NOR gates, so this is a NOR gate, two inputs NOR gate. I said the programmable logic array device, all the gates inside are NOR gates, even though we may have an AND array and an OR array. Of course, inverters you know that NOR can be converted as an inverter, NAND can be converted as an inverter. We know all that from our previous course on digital design. So now I have to tell you how I can get whatever function I want for F1 and F2, F3 whatever, using the inputs A, B, C, etc., using only a complete NOR gate combination. How is it done within the device? Let us take one of the example we took. I had 3 functions F1, F2, F3 and 3 inputs X, Y, Z. I am going to take the first one of those functions F1 as XY or X bar Z. This is the F1 of the previous example. Now since these have to be NOR gates, I have no choice, and this has to be an OR gate. I can only connect a NOR gate to another NOR gate. So I have to do something in the input and something in the output to manipulate the whole thing. I do this by connecting inverters. So I have an inverter at each of the input. If there is an inversion required, I put an inverter. If the inversion is not required, I put a double inverter. That means here it is X, I put an inverter X bar, Y bar. This is X, 2 inverters, so X, Z, 2 inverters Z, is Z with an inverter Z bar. So the output here is X bar or Y bar whole bar, X bar or Y bar whole bar, same as XY. You know that from De Morgan's theorem, again from the first course on digital design. Those of you who are watching this series, I assume that you are very clear about the first course on digital design, because I am going to use a lot of results, going to make a lot of assumptions. So if you are not familiar with basic digital concepts, I recommend strongly that you go through the digital design course completely, take a standard textbook or take a standard video series, look at all these chapters, make yourself very thorough, only then you can get the full benefit out of these lectures. So now we have X, similarly you have, I am not going to do everything, similarly it is going to be X bar Z, because I have X becomes X here, Z bar, so it gets an inverter, and now this NOR gate with an inverter becomes an OR gate, so an output is X Y or X bar C, which is F1, X Y or X bar C. So this inverter is taken care of, inversion is taken care of by this inverter. So this is the philosophy of using NOR gates throughout in implementing whatever function you want. So if you go back to the example we did, F1, F2, F3 with 3 inputs X, Y, Z, 3 outputs F1, F2, F3, this is what the circuit is going to be. I am going to have these are the inputs, an inverter. This was the original inverter which would have required in the original configuration of AND OR combination. I use X bar, Y bar, Z bar with an inverter. Now I am putting an extra inverter, that means this becomes X bar and this becomes X bar which is X. So this is X bar, this is X bar, X, Y bar, Y, Z bar, Z, and because of the same logic of the inversion of the inputs, because of the NOR gate, with this switch, the switches implement the NOR gate function as I just now explained. Even though X bar is connected to this, Y bar is connected to that, because of the inversion this becomes an XY. The same logic I talked about earlier. Likewise this X and this Z bar connected makes it X bar Z. This is my product term P0, this is my product term P1, The third product term P2 is y bar y, which is gotten by y. So, you do not have to worry about this y bar y and all that. If you completely remove this, you will feel very comfortable, because one inversion, another inversion, all that, if you do not want to get confused, you simply say this is x y, so I get x y. This is x bar z, so I get x bar z. That inversion takes care of it. Here it is y, so I get y. Here it will be y bar z. So, this will be further same type of NOR gate configuration, will give me the required functions, but I need an inverter finally. That inverter, the inverter of the OR gate, the NOR gate inverted into an OR gate, that inverter, these inverters correspond to that. So, there is an OR gate which I am not showing, a NOR gate and this. So, here will be a there is no point in showing it, because this NOR gate is only symbolic representation. The actual circuitry comes because of the, so I do not want to really show this because it will only confuse you. This was in the original drawing, schematic, it is a schematic, it is a schematic, but now this is a real drawing. So, because I am going to pull this down, 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 I am going to pull this down. When I am going to pull this down everything, this becomes NOR with an inverter becomes F1, F2, F3. So, this is the actual way it is implemented inside. This is not hardware. This, as I said, I am not going to talk too much about the implemented technology aspects for programmable logic devices, but this is a circuit technique we are using, because I am given a function of AND OR inverter. I am asked to implement it using NOR gates. I need to have this type of circuit technique. So, the circuit technique of converting the AND OR inverter into a NOR logic family is what I wanted to explain to you using this technique. This is the design using programmable logic array. So, we have now today seen PROMs, read-only memories and programmable read-only memories, how to implement functions using that, also saw programmable logic arrays and how to do programmable logic arrays implementation of digital systems. Thank you.